tell us about teaching functional programming languages to the masses, and in particular, how to have meaningful grading, because apparently the students never do what you wanted them to do, and they always find wrong ways to answer the correct question. So input-output is not enough to do some quality grading.
Thank you. Hi, everyone. I'm really excited to be here today to talk to you about automated grading and the role it can play in teaching functional programming. So at McGill University, where I'm from, we have a course that computer science students can take in their second year. And in this course, we teach them functional programming using OCaml. And over the past decade or so, we've had a huge increase in enrollment. We now teach around 600 students a year. So as we get more and more students, it takes us longer and longer to be able to grade all of their assignments, to the point where sometimes students end up waiting weeks to get feedback on their code. And at that point, they don't really care about it anymore. They don't really feel compelled to take that feedback into account. And so a valuable learning opportunity is missed. So last year, we made a big change to the structure of our course. We started delivering assignments and grading them using an automated grading and online programming platform called Learn OCaml, which was introduced at ICFP in 2017. Learn OCaml lets students work on their assignments and run OCaml code right in their browser. And it allows instructors to write automated graders so that students can get instant feedback on their code whenever they want it. So let me show you an assignment we gave our students last year using Learn OCaml. We gave them an assignment after we had introduced them to data types and pattern matching in class. And now we wanted them to practice this concept by using user-defined data types to model playing cards. Over here in the top left, you can see some preset definitions. We've defined a data type for suits and a data type for ranks. And then a card is just a pair of a rank and a suit. On the right are the instructions for this exercise. And for this question, we've defined an ordering on suits. And we've defined an ordering on ranks. And we give the students some pre-implemented functions that will compare two suits and two ranks according to this ordering. And now we specify an ordering on cards, which is just a simple lexicographic ordering, where we compare two cards by first comparing their suits. And if the cards have the same suits, then we go on to compare them by their ranks to decide which card is bigger. And so the question for this exercise is, write a function greater or equal card that takes in two cards and tests whether the first card is greater than or equal to the second. So here on the left is a space where I can write my solution. And let me show you how several of our students approached this problem. So I'm a student. I've never seen functional programming before. My only experience with programming is in something like Java. So the first thing I do when I see this question is I immediately pattern match on the cards, because that's what we just covered in class. So I extract the ranks and the suits. And then I read the description, which says, a card C1 is greater than a card C2 if the suit of C1 is greater than the suit of C2. So I say, they gave me a function for comparing suits. So I'm going to use it. And so I'm going to call this comparison function. And if the function returns true, that means the first card is bigger than the second card, so I should return true. And otherwise, I will keep reading. Or if C1 and C2 have the same suit, and the rank of C1 is greater than the rank of C2. So next, I will check, do the two cards have the same suit? And if so, I need to compare their ranks, and I have a function for that too. So I will call it. And if this function returns true, then that means the rank of the first card is bigger than the rank of the second card. That means the first card is bigger than the second card, so I return true. And otherwise, it returned false, and the rank of the first card is not bigger than the rank of the second card, so I return false. And then if neither of these apply, I'm finished reading the description, so I return false. So now that I have an initial solution to my problem, I can run the grader. And the automated grader is going to generate some random examples and apply my function to them and test whether these outputs are correct versus a reference solution. And so here the grader tells me that I seem to have an issue when I'm comparing two cards of the same suit. And I think several of you noticed while I was writing the solution that I was repeatedly neglecting the difference between a strict greater than comparison and a greater than or equal comparison. And so this first case was incorrect. So I know how to fix that. I will just make sure that my two cards are not equal. And now I'll run the grader again. And this time, my code will pass all of the tests. The grader gives me full marks. So I have 100%. I'm satisfied with my work. I think I did a great job. As far as I know, I did everything I was supposed to do. But as I'm sure you've all noticed, my code is really, it's not that nice. And I don't even know that it's not that nice. I got full marks. So what went wrong here? I would describe it as there being two main issues. The first is that I didn't really do any of my own testing or debugging or really thinking about the problem. I just read off the description, wrote down some code, and relied on the grader to debug it for me. And when the grader pointed out an issue with my code, I just threw in a quick hack so that I could satisfy the grader and get full marks. And the second problem is that I didn't get any feedback on any properties of my code besides just its correctness. So I missed out on the chance to become aware of and learn more about good functional programming style. And both of these problems come up often when instructors try to introduce automated grading into their courses. And so we spent the past several months exploring how other instructors have tried to handle this problem and see what kinds of fixes we can bring to LearnOCaml. So let's talk about the first point. We found that a lot of our students tended to treat their assignments as kind of a game of trial and error between them and the grader, because the grade button is just always available to them, and it's so tempting to just overuse it. And it's really a bit of a fine line for us to walk, because on one hand, we do want students to have access to this instant feedback, because it lets them incrementally develop their code and address and correct errors in their understanding right away, instead of getting feedback weeks later when they're no longer really going to incorporate it. But at the same time, one of our big goals is to teach our students about the importance of reading and fully understanding a specification, and encouraging our students to follow good testing practices and to value this as an important part of software development. So one way a lot of instructors try to tackle this abusing the grader problem is just by limiting the number of times students can run it. And unfortunately, there's some technical issues with how LearnOCaml is implemented, with how all the grading runs locally in the browser, that makes this pretty difficult for us to do in a way that's not really easy for students to get past. And more to the point, what we would really like to do is to actively try to change our students' attitudes about testing and have them value testing as, in fact, a first-class part of software development. And so what we would really like to do is make writing tests a part of our assignments and be able to grade our students on those tests. And so the question we asked was, how can we leverage the automated grader in order to be able to grade our students on the quality of their test suites? So the answer we settled on is a variant of mutation testing. And if you haven't heard of mutation testing before, let me show you how it works with a simple example. Suppose I wanted to write a simple power function on non-negative integers. And so I have a reference implementation where the double star you can just consider to be an integer exponentiation operator. And I, a naive software developer, have written a test suite for this function that I believe to be sufficient. I've written a test saying that pow of 4, 1 should return 4, that 0 to the power of 5 should be 0, and 2 to the power of 2 should be 4. And if I were to run these tests on my implementation, it would of course pass all of the tests, because my implementation is correct and my tests are all correct. But now say I made a mistake when implementing my function. Instead of the exponentiation operator, I instead put in multiplication. So I want you to take a second and think about what would happen if I ran these tests on my buggy function. And of course, the answer is my function would pass all of these tests, because 4 times 1 happens to be 4, 0 times 5 happens to be 0, etc. So my test suite is not good enough to be able to distinguish exponentiation from multiplication. And this may or may not be a bug that we're interested in our test suite actually being able to uncover. But let's say we are interested in it. Then how can we make our test suite better so that we can detect this bug? We can add another test case. So I will add a test saying 2 to the power of 3 should equal 8. And now if I run this improved test suite on my buggy function, it will fail the last test. And so my function will be exposed as buggy. And so the general idea is that we can try to evaluate the quality of a test suite by seeing what kinds of bugs the suite can expose. So we have implemented a variation on this in LearnOCaml. Let me show you how it works. So here I have my power function, as before, and I've specified some tests for this function. And we allow a test to just be given as a list of test cases, where each test case is just a pair of an input and an expected output. So these are the tests that I showed you just now on the slide, saying 4 to the power of 1 should be 4, 0 to the 5 should be 0, 2 to the 2 should be 4, and 2 to the 3 should be 8. If I run the grader with the mutation testing extension on this code, it's going to do several things. First, it's going to run all of my tests against a reference solution to ensure that they're correct and that I actually understand the specification of the function I'm supposed to be testing. And once it verifies that all my tests are correct, it's going to run them against some buggy implementations that are specified by the instructor. Here, the instructor has put down 2 buggy implementations. The first one is the one we just saw on the slides, where the function performs multiplication instead of exponentiation. But there's another bug that my test suite is not able to uncover, and that means there's a deficiency in my tests. And some of you may have noticed that we are doing integer exponentiation here, non-negative integers, but I missed the rather important base case of exponentiating to the power of 0. So I'm going to add a test case saying 4 to the power of 0 should equal 1. And now, when I run the grader again, it's going to rerun my tests against these buggy functions. And now I'm able to expose the bug in the second implementation, which does not correctly perform the base case. And so by letting instructors specify which buggy implementations they put into their graders, we can evaluate students and decide exactly what kinds of cases we want to make sure they're testing in order to award them full marks. And something similar to this has been done at the University of Michigan for a computer organization course. And they've reported really positive results on how this affected students' attitudes towards testing and the quality of their tests. So we thought this was a really good solution to integrate into LearnOCaml. Now let's talk about the second issue, which is that the LearnOCaml libraries and examples and documentation, and in general how people tend to think about automated grading, focus largely on a program's input-output correctness, which is only natural because that's a relatively simple and intuitive property to grade automatically and to give automatic feedback on. And LearnOCaml does give us access in our graders to the student's code AST, so we could write syntactic checks on our student's code. But this tends to take a lot of effort and a lot of code to achieve. And so our second big goal is to make it easier for instructors using the LearnOCaml platform to be able to write powerful and expressive graders. So one thing we've been working on a few things in this regard. One of them that I'm going to tell you about today is an extension for giving students suggestions on better functional programming style by giving them suggestions on how best to use certain functional programming constructs. So for an example, here are some snippets of code that beginners to functional programming tend to write. They'll write an if expression where the branches just evaluate to true or false, or they'll compare Boolean expressions to true or false instead of using just the expression or its negation. We've observed that students tend to do this kind of thing because they don't fully understand the constructs in question. In this case, they aren't 100% sure about Boolean expressions and how they can, in fact, insert them anywhere in their code where a normal expression would go, possibly because they're used to just using Booleans as a tool for regulating control flow constructs. And so we've written a framework for defining style checkers that will go over a student's code and give them suggestions on how it can better be written. And I'll show you how it works. Here is my beautiful greater than or equal card function that I wrote at the beginning of the talk. And I've equipped this grader now with the style checking extension. And it is going to give me a report with a lot of issues. It's going to point out that I've written a match expression with a single clause because I forgot that I should instead write this as a pattern matching let. And it's going to tell me that I've written an expression where I compared a Boolean to true instead of just using the Boolean expression, and that I've written an if expression where the branches were just true and false instead of just using the condition itself. So if I go and I apply all of these suggestions that the style checker has given me, I end up with code that looks like this. And now I can iteratively rerun the style checker, and now that the structure of my code has been simplified, it's going to give me one more suggestion. And this time it's not going to take marks off for this. This is just a suggestion that I can choose to apply or not. And it's going to tell me that my if expression, where I had a constant false in the else branch, could just be written as a conjunction. And if I choose to apply the suggestion, I end up with code that looks like this, which it's not perfect, but I think we can all agree that it's miles better than what I started off with. So aside from the style checks I've showed you here, we built in a bunch of other checks into our framework, which are listed on this slide. And we made our framework easily extendable so that instructors can implement their own custom style checks. And this was inspired by HLint and other tools for code refactoring that can be really useful for beginners to a certain language to learn good style in that language and to understand common idioms. So if you'll recall, I've talked about two main goals we were working towards with LearnOCaml. We wanted to encourage students to follow good testing practices, and so we added a mutation testing library that allows us to grade students on the quality of their test suites. And we wanted to make it easier for instructors to write powerful and expressive graders. And so we've been adding our own powerful static checks to the LearnOCaml libraries. And there's so much more to be done, and we're really excited to see what directions we can take this in, because we think LearnOCaml has so much potential for teaching functional programming. It runs all in the browser, so it's really accessible for students regardless of computing background, or even if they don't have access to a computer at all except at the library. And it gives students instant feedback, which encourages iterative development. It encourages them to keep developing until they have a completely correct solution, which can be so good for their learning experience if we can have them use it properly. And the included libraries make it easy for instructors to implement randomized testing for their students' code. And with our extensions, we're hoping to make it easier for them to implement other things as well. So I hope you'll check it out. We have a live demo of the platform with our extensions, which you can find at the first link. And we're working on creating a repository of automated graders for instructors that are new to the platform to get started with and use in their own courses, which you can find at the second link, along with the status of the project and a link to the LearnOCaml mailing list, where we will send out an announcement once this repository is available outside of McGill. So I really hope that this talk has gotten some of you excited and inspired about the idea of using LearnOCaml as a teaching aid in your functional programming courses. Because above all, our aim with this project is to promote functional programming education and to make it more accessible to teachers and students alike, both in our community here at ICFP and beyond. Thank you.
Thank you for bringing functional programming to the masses. There's a question that seems to be on everyone's minds, and that's number one by a large factor on Slido. It says, your demo looks exactly like an interact with Coq. Do you think this work has implications on proof assistant design? Or in other words, banging at the thing until it says yes is what I do for a living.
Well, so the work we've been doing is like specifically aimed at novices. So I guess I haven't really thought much about how we can work with introducing novices to proof assistants. I've been focusing a lot on OCaml here, and I'm not, and yeah, it's not something we've explored.
All right, let's move to questions from the audience. There was a first one here.
How do you handle code that doesn't compile?
So the LearnOCaml platform, it includes a compile button that you can click to check if your code compiles or not, and the grader will only run on code that compiles and type checks. So we don't need to handle it in our extensions. So yeah, the idea of dealing with code that doesn't compile is an interesting one, and there's some work on that, for example, like working with type tools in the Hazel language that we're interested in looking at and seeing what we can bring to LearnOCaml.
All right, there was another question over there.
Students often circumvent the providing tests challenge by finding a black box online that they can plug in inputs and get outputs, or maybe they just go ahead and write a correct version of the function first, and then they just do it themselves with their own implementation. They generate a huge list of tests that they then plug into the thing. So I was wondering if you have any suggestions for how to combat that issue.
So one thing the way we plan on using the mutation testing extension in the next term is that we basically plan on making it so that the students need to write the tests first, as in test-driven development. And we will not show them the results of the automated grader running on their version of the code until they have they've exposed a sufficient number of bugs. And so we're hoping to see how that goes.
All right. I'm switching to a question from Slido. For the style checks, do you find students fall into common pitfalls, or that they come up with varied, inventive ways to write terrible code?
Well, so many of the checks that we've implemented are the kinds of things that we often see. There's also an issue that takes a lot more thought to think of how to solve it, which is that students will basically use references in order to basically try to imitate imperative code in their programs, and that's a bit harder to detect than some of the simpler transformations we have here. And so there's a lot more thought we want to put into this in order to be able to add more kinds of suggestions to this framework.
All right, we have 3 questions from the audience. Let's start with Matthias.
I would like to point out a tool that has been around for several years, probably a decade, a practice that we had since 1997 or 96. Submit the tests first and have them reviewed by peers, then code, then run all tests on all programs. That way you get all the students to see what some other people do. They get an idea, they get a practice of reviewing things. The tool is called Captain Teach. It was published in educational forums by Sherm Kirschenmörgel and Joe Politz about 2 or 3 years ago, but it's been around for 20 years, something like that. That's an answer to one of the questions in the audience. I have a question, and I'm really, really happy about your work. I think that the most important point you made is that correctness is overblown. And what's really going on is, I think that what we overlook when we have all these talks on correctness at ICFP is that the actual cost of software is in maintenance. Like adding features, removing features, doing certain things, evolving the program. Can you imagine using your style checker combined with the mutation tester to have students evolve programs? One of the things we do in how to design programs is showing students systematically over the course of the semester how to evolve a program 4 times with feedback. I believe you might be able to combine your features. So can you imagine that?
Yeah, thank you for making me aware of Captain Teach. I hadn't heard of that one before. And yes, we are very much inspired by Dr. Racket and the great features that it provides for students for their learning. And a lot of our future plans are inspired by Dr. Racket as well.
Right. We have a question from Jeremy.
Hi, that was very nice. But I'm rather curious as to why the style guide guided the student towards introducing a conjunction there and stopped before introducing a disjunction.
Yeah, over here, right?
Yeah.
So the reason it didn't suggest that is because it's detected that these 2 expressions over here are kind of more complicated. And so introducing a disjunction there, it's kind of likely to make the code actually a bit harder to read. And so it's decided not to make this suggestion because these expressions are just kind of too deeply nested.
So it's not trying to make the code as short as possible.
Right. It's really just trying to teach them, make them aware of good style practices.
All right. While we swap speakers, we're going to take one last question here.
As part of this, are you measuring like the effect of this on students beyond just that you're doing it? And in particular, I'm wondering, like you're making particular concrete suggestions of style, and do you know, is the rest of their style improving? Are they learning? Are you sort of measuring over the whole population? Like, what are they doing? Or are they just saying, oh, I'll make this tweak and now the thing will pass?
So that's kind of a common concern that's raised when instructors add style checkers, which is that students will just blindly apply the suggestion. And from what I've read, people have basically hypothesized that students will they'll come up with some intuition behind these rules when they're applying them. And so they'll like have an idea of what this actually means when they repeatedly apply them. And that these kinds of tests, they tend to make they find that students become more aware of software quality issues as a whole when they're exposed to these kinds of things, because generally, like a lot of them they're new programmers, they're not really aware of this, they haven't had to work with other people's code a lot. And so it kind of raises more awareness about it.
But you're not measuring that.
We plan on measuring the effects this has on students over the next year. Right now, we're just going off of results from a lot of previous studies.
All right, I think we should wrap up. I'll just mention the most thumbs up question, which is more of a remark on Slido, which is that abusing the grader is test-driven development, so you're actually teaching them real, strong industry practices, so thank you.